Where's your phone? Set alarm. Oh yeah, you don't have it. That is rough. All right, so we're gonna go ahead and get started at this time. Just a couple of things that you should be aware of about this class period. The school is doing magnet recruitment videos today, so they always do that on the day of Club Rush. So that means that they are going to be coming into your classroom, most likely in this class period, maybe at the beginning of third period, and they're going to be recording the lesson. I think some of you were here when they did that last year too, like some guy with the camera set up comes in. And so they're going to record me teaching at some point during today's lesson, and they're going to record probably Sophia and Stefan in the back. So just so you have that heads up. If they don't come in this period, Jose and Kaylee, you'll be playing that game in the back, and they'll be recording you. So just FYI. Make sure that you are taking your headphones out at this time. If you have AirPods, take those out. And if you need to sign into your computer to see the Google Meets, please feel free to do that. Other than that, we are going to go ahead and get started. Today's lesson is a important one, as we are going to see why we had to define all of these energy changes and what that leads to. So, first, I'm going to call the bell work. Yesterday, AS did not get their point for the first time.
Yeah.
Oh, so sad. So,
Just need a little more sabotage, and then we could win. Just a little bit, you know, nothing too severe.
All right, let's see who this is for.
Just give them misinformation.
No, yes. But the board has already been delivered by Sophia. Sophia, somebody said they were picking up the board for Club Rush. Who did you give the board to?
Okay.
Who did you give the board to?
Oh,
Okay. So we're good.
Yeah.
Someone just don't want us to get lost. All right, so this is for Sarah was already called to speak.
It's big. Why is the wheel like so?
I don't know why he's choosing the same people, but it is for Samuel.
So what day did you
I think Sarah's been called like 3 times at least this year. Picking on you.
I think it's called.
Maybe 4 times?
It's called the last 3 days.
Sarah? That's crazy. Okay,
5, 6,
6.
7?
No, 6. All right.
Teacher, pardon the interruption. Some keys have been found. If you are missing your keys,
Uh-oh.
please come see Ms. Bledsoe in the main office to claim them. Thank you.
Uh-oh. All right, you are at 9 points now. Woohoo! All right, so before we get into today's lesson, which is on the Born-Haber cycle is what it's called, we're really going to learn how to calculate lattice enthalpies and enthalpies information when given lattice enthalpies. Let's go over the bell work and let's go over some announcements. First off, next week, I won't see you until Wednesday. Why not Tuesday? Does anybody know?
No school.
So if all goes well, I do intend to have a lab that day on Wednesday for you. Hello, this is Ms. Fleet. Sabrina, do you have the board? Mr. Lizarov is asking.
Yeah,
she said she gave it to Sam Gomez.
she didn't want to.
Okay. No problem. All right. So, Club Rush stuff. It's one of those days. So where was I at? Oh, Wednesday, lab, fire, hair back, no Crocs. I think that's pretty simple, right? Wednesday, fire, hair back, no Crocs. For Wednesday. So make a little note. I'll try to remind you on Google Classroom, but I'm not sure if everybody has notifications. So please make sure that you're not Crocs for Wednesday's class. It's the next time you see me. Okay, got it? Wednesday. All right, that's the plan if all goes well. I'll be setting up on Monday after school. I won't actually physically be in the building on Tuesday because I'll be going to process science for our STEM challenge training for that. So just so you're aware. So whatever we're doing for Wednesday morning, I'll be setting up Monday after school. Monday, don't forget, we also have tutoring. So if anything in today's lesson is confusing, you're working on the homework and you're like, oh boy, then come on Monday's tutoring and I'm here for an hour to help out after school. All right, so that's that. Let's get to the bell word. First thing is standard enthalpy change of atomization of silver. Many of you did fantastic on this bell word, I noticed, but we're going to go ahead and review it anyways, just in case you missed a mark or two. Where were those marks at? Ag solid goes to Ag, yeah, that's all you had to write. 1 point. Formation. Standard enthalpy change of formation of silver 1 fluoride. So this would be Ag solid plus F2, what is the state for that? Gas, goes to, what's silver 1 fluoride? And that's crazy that they actually gave you the oxidation number because they didn't have to. You're actually supposed to know that silver is +1 by heart. That's one of the 3 you're supposed to know by heart. So it's silver +1 with fluorine -1. So it becomes AgF, which is what state of matter? Solid. And this should be a 1/2 to balance it. And so that would be the point there. What is, why am I on I don't know. We'll go back to Bellwork 1, yes. Yes. The requirement for enthalpy change of formation is that you make 1 mole of product. That is important and relevant for today. That is. It is. All right, define lattice enthalpy, so, or energy. So what do we do here? And I mean, as long as you said the keywords, you get the marks. What are the keywords? So it's the energy change when what? 1 mole of 1 mole of an ionic compound. So it's only for ionic compound is formed from gas ions. So the other part is to say basically gas ions, so 2 ionic compounds, and you have just 1 mole. Every enthalpy energy change is always the energy change when. So make sure that you start with that as your response. Let's go back to Bellwork 1. This is from paper 4. Bellwork 1 is actually a question we did before in paper 2, a paper 2 practice question. Write an equation that represents the first ionization energy of hydrogen. So many of you got this. Hydrogen goes to hydrogen +1 plus E minus. What am I missing? Gg, right? And on the bottom, it says, why is there no second ionization energy? This is where I saw the most incorrect responses when I was checking. Hydrogen has how many electrons? 1. You cannot take a second electron away if there is no second electron that exists. If I only have $1 and you're trying to steal $2 from me, I mean, you can shake me down all you want. You're not getting the second $1, right? That's the situation at hand. Yes.
What did people put that were wrong?
That there were 2 electrons. Or they did they accounted for the charging correct. So there is only.
Was it you, Daniel?
You don't have to say. Don't say. There's only 1 electron. Don't out yourselves. All right. There's only 1 electron in hydrogen. So next thing, I have your tests. Unless you took it late, I have your tests ready to get back to you at the end of the class period, but you must remind me as I am tired and I may forget. It's Friday, but I have them. I have them. They're ready to be given back to you. What?
It's Friday.
It is Friday today. It's been a very long week. All right, so, but the good news for everyone is next week you have a day off on Tuesday, and the week after you have a day off on Thursday. So we got a couple of weeks that are a little bit less intense. And then we'll have a bunch of weeks after that are very intense. All right, so let's go ahead and get started. Today we're doing Unit 2, Part 2. You'll notice that the slides are printed 2 per. What does that mean? Take notes. Lots to draw today, actually. So for those of you who like, writing or drawing, it'll be a great day. We're going to go over something called the Born-Haber cycle. And so really it's just a very specific enthalpy cycle. Hello, this is Miss Lee. Ramon is not here. I put that in the attendance, right? He did not walk in late. All right.
The greatest gem packet was so small.
Okay.
Heard of this?
But that is the way life works. All right, so light work. So this is actually just a very specific energy cycle. So you're going to want to write that down. That describes the energy changes involved in forming an ionic compound. So we're going to detail from start to finish how we go from elements in their standard state to an ionic compound. So like you saw in that reaction I showed you by video last class when you took sodium and chlorine and you saw all that big energy release, right? What are the actual steps detailed in that process? What are the energy chains detailed in that process? How do we get there? And so today will be largely a math type lesson because it will have an equation. Bye, Dario. Bye. You're coming back? Oh, okay. So, it's a very specific energy cycle that describes the energy changes involved in forming an ionic compound. That's really what this is going to be about today. And so last class, we spent the whole class defining different types of energy changes. And so today we're going to go ahead and bring all of that together and what that's actually being used for. This unit has 6 lessons, just like the last one. So this is part 2 out of 6. Next class period, like I said, we're likely going to do a lab. I haven't decided yet whether I'm going to put a lesson as well. Last year I put the lesson in the lab on the same day, but because we're such a big group, I might not do that. So we'll see, depending on how things go and depending on how much practice I want you to get on this. But you will have a lab next class, most likely, as long as I'm able to set it up on Monday after school. And it will be with fire. And it will be a crucible lab. It will be a crucible lab. I'm just letting you know. All right, so objectives. What do we got to do today? We have to construct. What is that directive construct? It's like draw a diagram. It's design. And it will be a diagram. Construct and use Born-Haber cycles for ionic solids. And notice what they limited you to. They're going to limit you in the construct and use to +1 and +2 cations. You can thank them for that because the more the ions are, the more electrons you either give or take away, the more steps there are in the cycle. So that means +2 charges are more steps than +1 charges. Same thing for -1 and -2. Carry out calculation. That means we need our calculators today. We're going to be doing math involving these Born-Haber cycles. And then this we actually already did. I just forgot to take it off. We did this last class. I was able to fit it into last class. Where we looked at charge density and the effect of size and charge on the numerical value of lattice enthalpy. We did actually cover that last class. So let's get to it. Like I said, your notes you can see are really big today. There was one type of question though, I remember that I wasn't able to fit into last lesson, or I didn't, that I have right here. This was one of the objectives last class we didn't cover, It's technically something that you could get on your own, but we're gonna go ahead and cover it together. What is the trend in the electron affinities down group 16? So what would the trend be?
Decrease.
So first of all, it does decrease. So I'm not correcting you. But what is the general trend in electron affinity? What's the general trend? Go ahead.
The bigger the radius, the less the electron affinity.
Why?
Because
Shielding.
shielding.
Yes. Yes.
And that's a density, current density.
So I'm going to give you the answer shortly, but what is electron affinity again? What is that? Like when we're talking about electron affinity, what are we talking about?
The energy they can receive an electron.
It's similar to electronegativity, but they're not exactly the same. The trend is the same as electronegativity largely, because electronegativity, it describes the ability for an atom to gain an extra electron, and here it's the energy change associated with that atom gaining an electron, right? So what electron affinity actually is it's the energy change, welcome back, associated with, so energy change associated with adding an electron. And what did we say for first electron affinities? Were they endothermic or exothermic? They're exothermic, right? Why? Because when you add an electron, something that has a high electron affinity, it's going closer to a noble gas, it's going to a more stable state. And so therefore it is releasing energy as a result. And so here are the marks. And this is the one that I don't think anybody had said. The way you have to describe it is that the electron affinity, instead of using the word decreases, they're going to, and it's going to be a thorough line through this unit, meaning you have to answer the same way for a lot of questions, and it does end up being confusing for people to understand, but we'll see if we can do a good job. Electron affinity becomes less exothermic down the group. Let's wrap our brains around that. Does that make sense?
That means it releases less energy than the group.
It means as we go down the group of the periodic table, it releases less energy to add an electron. Do you want me to write that down? As we go down the group, I'm going to write it on the side, right? Because it's not actually part of, it's just me rephrasing the answer, yes.
Oh, so it's easier to lose an electron.
As we go down the group, what did I say? As we go down the group, less energy is released, right? Less energy is released as a result of adding an electron. That's a rephrasing of what the Mark Stevens says, of adding an electron. Does that make sense? If less energy is released, does that mean that this is an increasing trend or a decreasing trend? It is a decreasing trend. So when you said the electron affinity decreases, that is true. But they expect you to phrase it by what's happening with the energy. Is there more energy released? That would be increasing. Or is there less energy released? That would be decreasing. So I can even write that on the side. So decreasing here means, because this is where it gets a little bit confusing with the terminology. Decreasing means less energy released, the decreasing trend. And here, increasing would mean more energy released. Which one's favorable?
Decreasing.
Like, which is more favorable? Less energy released or more energy released? More is more favorable, right? So we're saying that as we go down, the trend decreases. It becomes less favorable to add an electron as we go down the periodic table, which you should already know. As we go down the periodic table, it's more difficult to add an electron as the, was already mentioned, you said shielding. And so they said atomic radii increases, or you could just say more shielding. So the second part was to say atomic radii increases, but in parentheses, they said you could have just said more shielding. So as I go down the group, there's more shielding as there's more energy shells. And then there was another point you had to make. What do you think the other point is? Oh. Why does more shielding cause less energy to be released? The nucleus isn't as attractive. That is the other part. So the way that they said it is there's less nuclear attraction for the added electron. The electron's farther away, right? So if there's less attraction, that means less energy is being released. If there's more attraction, that means more energy is being released. Yes.
Could you like go over how shielding works? Okay.
How shielding works?
Yeah.
Sure. I may need to add an additional slide. Like you could write it on your paper, but I'm running out of space here. So I'll just add an additional slide. Let me know when you're good with this. And I can redefine shielding. I'm going to keep it because unlike last year, there's only one class period, so I don't have to delete the slides to reteach the next class. So I can just save the slides if you need to go back and copy something later. Unfortunately for free, I have to if I have to leave, I have to delete everything. But for us, we're good. All right, so shielding. What is that again? If I have, let's say, sodium, right? Sodium has how many protons? It has 11 protons, and it has how many electrons? Also 11. So 3, 4, 5, 6, 7, 8, and then, oh no, and then the last one. That's sodium, right? Let's take a look at potassium. All right. So potassium, how many protons and electrons here? 19. So 19 protons, and then 1, 2, 3, 4, 5, 6, 7. Oh my gosh, I didn't write that right, but whatever. 1, 2, 3, 4, 5, 6, 7, 8. Oh no. I'm gonna count in my head now. 4, 5. See, I did good there. All right, so concepts being which of the electrons here is more attracted to the nucleus? That valence electron or this valence electron?
First one.
The first one. And so there's really two reasons. One is the distance of that electron is closer to the nucleus, so it feels the nucleus more strongly because of that. And the second factor is because here there's only 2 layers of blocking electrons. Here there's 3 layers of blocking electrons. And all of these electrons have repulsive forces. So here we have increased repulsive forces, which by itself decreases attraction. So if this electron is repelled by these other electrons, it's not feeling the positive nucleus nearly as well. So it's less, we say it's less tightly bound to that nucleus, which means it's easier to take away, which means a lower ionization energy. And if we were to add an additional electron here, it would not be favorable. It wouldn't for several reasons, but it wouldn't be favorable partially because you got all these negative electrons here, and electrons repel other electrons. And so that's the concept of shielding. Kind of make sense?
I think so.
Okay, so I'll leave this here just in case we need to revisit it for anything. But make sure you have this down. I'm trying to do my best to describe how what we know links to what Cambridge is saying in the Marx even. This concept of energy being released can be a confusing one because we're going to be talking about exothermic. Exothermic is negative. And whenever we get it to negative, everything gets opposite of what you think it is sometimes. Like it gets a little confusing. So I'll try my best to slow down and track it down as we go through the lessons of this unit. Lesson 4 especially is very spicy with that. Lesson 4. I think the easiest lessons in this unit are 5 and 6, crazy enough. Like the last 2 lessons of the unit are the easier topics in my opinion. It's spontaneity, entropy, and Gibbs free energy. If you have no idea what that is, but it's basically how much energy is there for a reaction to take place. All right, so here it is. This is what we will be looking at today: how to construct a Born-Haber diagram. And so it's going to be a large diagram where you highlight all the processes that take place in order for you to get from your initial state, which is elements in their standard state, to your final state, which is the ionic compound that is formed. So how do we get from elements in their standard state to the final ionic compound? It doesn't happen directly. It happens in a series of steps. You can almost think of it like a mechanism, right? Because it happens in a series of steps. And those steps are going to be, you have to turn both of your atoms into gases. Single gases. That's called a process called atomization. And then after you atomize, you then have to take electrons away from your positive ion and add electrons to make your negative ion. And then once you have those ions, then they come together to form the final ionic compound. And them coming together is called the lattice enthalpy. So we'll be taking a look at tracking all of these different energy changes today. And what do Cambridge questions look like? I pulled this off online, like from online. This is not exactly how we'll write it with the arrows at the top and the bottom. But I do want to use this as an example. So example reaction. Forming NaCl. It's about the most basic reaction we can get, right? We looked at that last class. What is the standard state of sodium and the standard state of chlorine? Na is a solid. And chlorine is a gas. And it's a diatomic gas. In order to get to here, what does sodium have to have done? In order to get from sodium solid to sodium with that plus charge, what does sodium have to have done? What energy changes have had to have happened to sodium? It had to lose an electron. That means you have to account for the ionization energy, and you have to turn it from a solid to a gas. And so Na would go from solid to Na gas. What would we call that? Atomization. That would be called delta H, and I believe here they use AT.
Why would any answer we can look at?
Because in order to form the final ionic compound, they have to be ionized gases to come together. That's the lattice enthalpy. Yes.
Well, the only way of forming a unit is
The only way you can track the energy changes is to get them to ionized gas.
And so this reactor is without taking those.
The activation energy required, it depends. Like if you spark them, you need a source of energy to start that reaction. But then with that energy, it pushes them back up to ionize. If you have enough energy, it pushes them up to ionized gas. So the solids themselves, like if you smush two solids together, generally speaking, in most cases it won't work. Even something super reactive like calcium carbide needs something like water to, help it to explode. It needs some kind of media for that to happen. So that's why you're noticing the processes take you go into an ionized gas. And although you don't actually see that because it happens so fast, they track the changes this way. So what is the energy associated with this change? That's what I'm going to be describing now. What does that say there? Because it's on the chart. 108 kilojoules per mole. What else did I say we had to do? So you go Na solid to gas. The next step they do always is they atomize the other atom. So atomizing chlorine, what would happen there? 1/2 Cl2 gas goes to what? What would that become? Just Cl. And what would that atomization value be according to the chart? plus 122. Last lesson, did I mention there was another way to come up with this value that isn't on a chart? There's a source where you could find out what this value is. Instead of using the atomization, you could have done 1/2 the bond energy. I'm going to take the time now, if anybody has their workbook out, to bring up something. Can I use yours? I had some forethought in the summer. And in the back of your workbook, right after the last lesson, I printed copies of the data booklet. So the data booklet is integrated into your workbook this year. On top of that, I put for the data booklet where that data is important, specifically which unit of study are you going to see it. And so the first page that has is the ionization energy value. So if you were given a Cambridge question by me that is before the year of 2022, they required students to use the data booklet to come up with the numbers. So ionization energies are found on that first page. If you turn the page to the back of the first page, the very next data table you get is something I gave you last year in advanced chemistry called the bond energies. Why am I bringing this up? Because if I give you an older question, you will need to refer to possibly get a bond energy to your data booklet. So you'll need the bond energies possibly. So look for the unit of study where it's at, and then you'll see the next handout says unit 3. So in your data booklet, there's a couple of things here that are going to correspond directly into this lesson for any pre-2022 questions. Okay, because they only repeat questions so often. So even though data booklets were taken away in 2022, if I give you an older question, you still have to be able to reference it to come up with answers. Now, how do you get the answers? Well, you'll see they provide the numbers in the question, which could be good or could be bad. Because what ends up happening, and I'll show you in your bell work next class, and it's probably going to show up in your homework too, when they give you all the numbers, you'll see them later on, like, I'm just going ahead. They give you all the numbers, right? Is there a possibility they give you extra numbers you don't need? That's a very real possibility, probability that they do that. And so, because they took the data booklet away, they wanted to, give you a different method. But anyway, so we're tracking energy changes. The first thing that we do in order to get from our regular compound, like from our regular elements in their standard state to the final compound, is we have to change each of our elements into gases that are single atoms. We call those atomizations. What's the next thing we have to do to sodium? It has to lose an electron, right? What would we call that energy change? So Na gas to Na plus 1 plus E minus, right? And that would be called the delta HIE, ionization energy. But it'd technically be the IE1. Why would it be the IE1? Because it's the first one. And do you remember that each ionization energy would be a different value? So if I were to take a second electron away, that would get its own energy value. So what is it here? They give it to us here. It's 496 kilojoules per mole. And then what do we have to do to chlorine to get it to where it needs to be, which is ion gas? What do we have to do to chlorine? Give it an electron, which is called the electron affinity, delta H EA1. It's in the game. I can't. It always completes in my head no matter what for the past like 15 years. And then what is it? Negative 349. Do you see it? kJ per mole. All right, so basically, looking at this graph, this is your start. This is your energy end. Is this overall reaction endothermic or exothermic by looking at it? This is the starting energy. This is the ending energy. Okay, I told you the delta H up. It's exothermic, right? Which means at the end, you're going to have 410 kilojoules of energy released. And so here's what the graph does. It tells you, okay, this is an energy input, goes up. This is an energy input, total energy goes up. This is an energy input, that energy goes up. Well, electron affinity, that's an energy output. It releases energy, so energy goes down. But because we had all these up energies and only one down, you've got all this space between here and our final energy of our product. And all that space there is called the missing piece, which is the Na plus Cl minus goes to NaCl. What's that called? The lattice enthalpy. So once you have Na plus 1 gas and Cl minus 1 gas, and those come together to form NaCl, this is called your delta H lattice. And they told us here that that was, and it's actually negative 787. I know what's wrong with that chart. It's probably the way that they wrote the cycle. 787 kilojoules per mole. But the idea here is that when you add up all of your energy changes, they should end up adding up to the enthalpy change of your reaction. Oh, they're pointing, yeah, well, I'm gonna point it down because that's how we're gonna do it when we do our own. Yes.
I don't understand why the ionization energy of sodium is endothermic.
Is what?
Endothermic.
Why is ionization energy endothermic? Take an electron.
Isn't it the more stable state?
Take an electron. Does that require energy? Always. It requires less energy, but it requires energy by definition. Ionization energies are always endothermic because you're always describing taking an electron away. Even though there may not be a lot of attraction, we say there is some attraction between this negative electron and this positive nucleus, because otherwise, why is it? If there's no attraction, why would it be there? Does that make sense? So there is an attraction you have to overcome to take the electron away. That's called the ionization energy. Good? Positive. And we learned that back in last year. Okay. Wow, that's a lot, right? That's a lot of equations. The good news is that most of the time, if they just ask you to do the math, you're just going to have to add all the numbers. But the careful thing is you're going to have to account for moles real carefully, meaning how many of each atom do you make in your final equation. Here the numbers are real easy because you're making 1 sodium and 1 chlorine. So everything is already in kilojoules per 1 mole. But sometimes you make more than 1 mole, right? So we'll get to that in a moment. So let's learn how to construct a cycle from scratch. To draw your own cycle, you're going to start by putting your elements in their standard states on the left-hand side. And I'm going to work with you on how to create this from scratch. We'll do a couple examples. Then you're going to add in all the other necessary enthalpy changes. Don't add in anything unnecessary. Only the necessary enthalpy changes. This is the order that they write it in for the mark schemes that I've seen is they do the atomizations first, which means turn everything to a gas. Then they rip the electron away from the metal, give it to the non-metal. So rip the electrons away from the metal, give it to the non-metal. That's the idea. And then you're going to complete the cycle by adding the enthalpy change of formation. And I'll show you how to do that. The lattice enthalpy. And make sure that if you're writing your arrows up, this is indicating an input of energy. And if you're writing your arrows down, this requires an output of energy. And the reaction will be exothermic. So let's take a look. Draw a fully labeled Haber cycle for BAF2, naming each step. So yeah.
How many much order those be?
I'm so happy you asked that question.
Like 2.
It's right here.
What? God. Dude.
Anyways, you choose whether you want to, go.
What the
for it.
Sigma?
What the sigma? We learned sigma and AF earlier this week, but All right. 2 marks. Anyways, so what would I start with here as my axes? What is on this axis? What do you think?
The Y value.
What's going up on the y-axis? What would always be increasing for your ionizations and your atomizations and then decreases? Something called your energy. Energy or enthalpy. You can write either energy or enthalpy. Before I start, what is the reaction for making BAF2? I want to have that on the side because that's what we're tracking, is the reaction to form BAF2. So what is that overall reaction? It is a synthesis. It's enthalpy of formation. So it's barium solid plus what? F2 goes to BAF2 solid. And we're not actually going to fit in the numbers here. We're just labeling the steps that we would have to follow to get I. For real this time? Or are you coming back again? Okay. That's the overall reaction. Agreed? So that's your reactants. So your reactants, you write them on, and I believe for the Cambridge, they write them on the top of the line. So I just want to sit and follow what Cambridge says. So I'm going to do BA solid plus F2 gas. Leave yourself some space. You're going to need a lot of space for going out.
Also,
Yes.
on like the exam at the end of the year, are we gonna be allowed to use pencil for this?
That's a great question. This classifies as a diagram. This is a diagram. Please use a pencil. Continuation booklet. Hope and pray. Yes.
Chance do they give these notes online so I can help them from my pod?
The notes are always posted online after the lesson with the recording. All right, good to continue? All right, so what is our product here? So this is our reactants. I'm just saying this is our reactants, right? The energy of our reactants. Where's our product? It would be on the opposite side, the right-hand side, because reactants in an energy diagram always go to products. Would the energy of the ionic compound be higher or lower? What do you predict? You should predict that it's going to be. I form an ionic compound. Is that higher or lower? Is that a favorable thing to happen? That barium gives up its electrons and fluorine gains them. Is that a favorable overall process?
Yes.
Absolutely yes. So it's going to be endothermic or exothermic?
Excellent.
Exothermic. Right? Delta H. What would that be labeled? BAF2 solid. What would this be labeled? Delta H what?
Formation.
Formation. So when they say label, they mean write delta H F. You do not have to say enthalpy of formation. You don't have to say all the words. The fact that you wrote this means you labeled it correctly. I mean, you can say few words. Exactly. All right. I would also give the sign. Get comfortable with giving the sign because you know that it's going to be exothermic, so you should write that it's negative. We don't have an actual number. We just know that it right now is negative. It should be negative. All right. So how do we get from here to here? That's what I just went over on the last slide, but now we're going to do it with an example from scratch. So what were the steps that I outlined? I did give you steps to outline it. Where do we begin? Atomization means turn them to gases. It takes less energy to turn something into a gas typically than to remove an electron from it. And so we turn into a gas first and then we rip the electrons away. So it doesn't matter what order you do, but we usually follow metal first, then non-metal second. So we would do delta H AT for which element? Barium. So I'm going to do delta HAT for barium. What would the value be, positive or negative? I'm turning from a solid to a gas. That should be an arrow up, which indicates positive. All right, so what next? Write a new line. Write the result. What have we done? We've changed the solid barium to gas barium. So now our result is Ba gas plus F2 gas. What comes next? So we're highlighting the process. All we did here was change barium solid to barium gas. That's the change. What's the next change that happens? Can F be 2? In the final, you're putting ions, single ions together, right? So this actually has to become Ba, and let me put my little line. Ba gas plus what? 2F gas. And what would that be? The delta H of atomization for which thing? Chlorine. And would that be multiplied by 2? Because you're making 2 of them. You know it's going to be a positive value. You should put the multiply by 2 there. That's what I meant by you have to know what the energy changes are. Look at the moles. If I'm making 2, that means whatever the number they give me is, it's going to be in kilojoules for every 1 mole. So I will have to multiply by 2. Trying to be careful here because when we mess up in the math, that's usually where the mess ups happen. What comes next? We atomized, we turned everything to gas. So now we ionize. And that's something that I usually like to say, atomize, then ionize. I don't know if it's confusing because when you ionize, that means for your actual metal, you're using the ionization energy, but for your non-metal, you're using the electron affinity. But you're ionizing them both. You're turning them both into ions. And so what comes next? We don't have numbers, so we just put arrows up. What are we doing now? How do we ionize barium? We change it from a charge of 0 to a charge of +1 first. So barium +1 gas plus 2F gas. And what would we label that change, energy change? Delta H IE1. Right? Yes.
You have to put the electron.
You do not. You could if you wanted to, but if you misplace one, that's a problem, right? So I usually just do that. Cambridge doesn't get their mark scheme, but that electron, those electrons are going to fluorine. Now, what's the next thing? Can we leave barium at +1? Or do we know better? Barium is right there. It has +2. So you have to do with successive ionization energy, the second ionization energy. You gotta do it again. Oh my gosh, how many arrows?
Is that the last one at least?
What?
Is that the last one at least?
We haven't done exploring yet. Plus 2F gas, delta HIE what? IE what? 2. Also positive. I don't know how picky they'd be. To be fair, the second ionization energy is always greater than the first, so the arrow would be larger. I made mine slightly larger, but like I said, I don't know how picky they would be. And then chlorine. How do you add an electron to fluorine? What is that called? And does the energy go up or the energy go down?
Down.
It actually goes down. So you write a line through like that. And now we're going to do an arrow down.
You're talking about.
I'm saying you're going to need room. Don't worry, there's plenty of pages coming to keep outlining this. Like, how much space do they give you on a finger exam? What's the result of this? This is going to be Ba plus 2 gas plus 2F minus 1 gas. And what's that called? Delta H. What? EA. Right? I'm just trying to erase. I don't know if my board's giving up on me. Maybe. And should that be positive or negative? Negative. All right, so all these ups and that's down. But we still have to get from, we have our ionized gas to our final compound. So what's the very last component? This right here, right? The energy difference between the ionized gas and the final energy of the compound, which is way lower. Yes.
You have to multiply the electron affinity by 2.
Yes. Good point. And everybody should add that in because I did that earlier. You should multiply the electron affinity by 2 as well, because I mentioned everything for fluorine would be multiplied by 2 when we get to the mass, because we have 2 fluorines made, not 1. Could you have figured that out just by looking at the compound made? You could. So you'll see later on when you get to the math, do you have to actually absolutely make this cycle every time? No, it's just to help you visualize what's going on. All right, so then what is this label? We're almost done. Delta H, LE, and there's only one of that. And what should the value be for Let's enthalpy? You need to know that it's always going to be negative. It releases a ton of energy. By definition, Let's enthalpy releases a ton of energy to go from the high energy gaseous ions into the solid compound lattice. They form together, releases a ton of energy in the process. This is worth 2 whole marks. Very exciting. You've already decided?
Yep.
Yes.
I'm just giving a speech.
They don't. like they didn't. And I mean, they didn't even write the energy on the y-axis, but I would, just to understand that that's actually what's going on. So it's what's on the inside is where the marks are at. All right, continue? Yes.
Delta H.
Yes.
So when you send table 1, would you put -1? That's
Just negative. Here.
Okay.
We'll look at the numbers later on. And then for the charge, it's -1. All right, so how do we feel about this so far? You want to try one? Well, try one anyways. Here you go. Then I'll work through one more try with you of some kind of situation you should be aware of, and then we'll get to the math. So try this one. I'll give you 5 minutes. Yeah, 5 minutes. That's a lot of time. See if you can try this one.
I'm also gonna ask for one with like all the actual like energy numbers labeled as well.
You'll see the math question shortly. So it says, write an equation to represent the Letsy enthalpy and draw a fully labeled Bohr-Haber cycle. You do not need the numbers, just the identification of which energy change, and then write on the top, like I showed you in the last one, what to do. All right, try this one yourself. Oh, no, I don't freeze those steps, unfortunately. But you can go back and do it later after I post them. All right, so. We'll skip the other your turn. Try this one. See if you've got the idea. I'll start writing the answer up in 2 minutes, and then I'll show you a situation. You just went straight to ion.
And I did become.
Wonderful. Didn't I just have one? You sent it. Remember, chase your thought process. Yes. Yeah, you got it. What? This is just how it looks coming from Cambridge as a question. So I wrote up the answer to the first part. And I'll start tracing the answer to the second part now for sake of time, because I do have to show you a unique situation. I need time to look at the math. So if you started with this calcium gas plus Cl2 gas, and you labeled that delta H atomization of calcium, they don't require that you actually put the positive or the negative afterwards, just that you've labeled it. Actually, the fact that you've written the arrow up is enough to say that that means energy up, energy going in, endothermic. So you don't, the only reason I wrote the plus and minuses in the next question is so that you understand when we do the math, why the numbers are either positive or negative. And so the next one would be the atomization of the chlorine. And so you would end up here with Ca gas plus 2 Cl gas. And I should know from my math that I'm going to have to multiply by 2 when it comes to the time to do the math, which is shortly. And so the next one is ionize, right? Delta H IE1 for calcium, Ca plus 1, like that. Then IE 2. And they know you're doing calcium because that's what you're changing. Whatever you're changing is what you're ionizing. So when I know I see plus 1 to plus 2, I'm ionizing that. Then line over down. You don't have the numbers, so it doesn't really matter how far you go down. Ca plus 2 plus 2Cl minus, and we label this the delta H EA, and we multiply that by 2. And then go all the way down to here, calling that the delta H LE, or they call it the delta H lat a lot of times. We call it the delta H lat. And I think I'd rather call it that because that's how they usually do it in our schemes. Delta H lat. Lat for lattice energy. All right, so there's one more that I wanted to show you because I think it's necessary that we discuss. What if there was a second electron affinity? Why is it necessary that we discuss that? Well, we got here electron affinity. The first one's negative, but remember the second one is positive. So you have to put another line up afterwards. Let's at least look at one example to see what that should look like. Ready? No? I'll pause. 30 seconds. You got it? How many marks is this worth? 2 whole marks. You want to know what else is worth 2 whole marks? Defining lattice energy. Just saying.
The first part was 1.
The first part was 1 mark.
So 2 of those.
Marks are not distributed. I mentioned that, right? Marks are not distributed in an even way, in my opinion, on a paper 4. Go find the ones that are easy first. Do not like look at the first question and be like, oh my gosh, that's so hard. Let me sit on that for 2 hours. Don't do it. If you look at it and you're like, oh no, skip it. Don't let yourself get stuck. I told you the story. One time one of my best students did that. All right, let's continue. Draw a fully labeled 4-Haber cycle for MgO. Let's encounter this situation. What happens if I have a -2 charge? So in this situation, we've got Mg, right? Plus 1/2 O2 going to become MgO. So remember, if they don't give you the equation, you should start with what is the actual reaction? What is the synthesis to make this ionic compound? It's also known as the delta H, F, the enthalpy of formation. And so where do we begin? I like to write that this is energy for good measure. I know my reactants have to be a little bit higher than my products. So let's start from here. What are my reactants now?
MgO2.
Mg solid plus 1/2 O2 gas. And I'm going to write my little delta HF down because I know that that's going to happen. And eventually I'm going to write it all the way over here. This is MgO solid, right? Energy release to get there. But now we need to fill in the rest of the story. So what do we do first? Going to be atomize the magnesium, right? So delta H AT for my magnesium. You don't have to specify that as long as you show in the next step that magnesium is gas. You just show the change, everything else remains the same. Yes.
I have a question. If they give us atomization energy, and let's say the non-metal has a lower energy, atomization energy than the metal, would we have to put it first?
I've never seen them do non-metal first. Like not lower energy to higher energy.
Just in theory, I'm sorry for getting on this tangent.
It's all additions, so it doesn't matter.
I mean,
But technically, whether you start by making your metal a gas or making your non-metal a gas, that doesn't matter. Because they're not interacting with each other yet. Right? You're just raising the energy in the process.
I'm imagining you're heating them at.
You could be. Each of these processes are in isolation until they come together, technically. All right, so the next one is delta H AT of the oxygen, right? So then that's going to be Mg. How many oxygens are here in this one? Just one, right? 1/2 of O2 is 1. So that means I do not need to multiply by anything. The delta H atomization would just be the number. Now what? Delta H IV 1. That takes us to Mg plus 1. I know some of you are probably starting to already run out of room. I apologize in advance. Delta H IE2. That gets us here. And now what? Now we go down. This is where it gets fun. Line down, delta H EA1, and that gets us to what? Mg plus 2 plus O minus 1 GGs. But now what? Now up. The second electron affinity is always positive, right? We talked about that last class. Adding a second electron to something that's negative adds energy. It'll be delta H EA2 and then Mg plus 2 plus O minus 2 GGs. Then finally, from here, you go all the way down to there, delta H lattice energy. I'll pause.
Doesn't seem that bad.
No, you just have to know what to do. I don't want you to be confused when you encounter it. So basically, you just have to create space to have that extra up arrow. Yes.
Would it be below the ionization energy, or
If you have the numbers, you can make that prediction.
if we don't,
Then
it doesn't matter?
it doesn't really matter. I'm just using the one I remember for sulfur where the first one was less than the second one. This was a lot different, so I think that's good.
But it's gonna get worse with the math.
I don't know that it's necessarily worse with the math. I don't think the math is that hard if you understand the process. Remember what I told you earlier before we started making the cycles? Literally all you're gonna have to do is add together all of these processes, the adenization, the ionization, and the lattice enthalpy. And what will all of that give you in total? The energy change of the reaction. And so that's upcoming next. Yay! We're gonna skip this one because I already had you do one that was your turn. For sake of time, I thought when I was rewriting the lesson last night that I probably put one too many. I just wasn't sure which one I was gonna leave out. So calculating. That's the next thing, right? We gotta calculate lattice energy using a Born-Haber cycle. And we can do this using Hess's law, which the cycle actually really just gives you Hess's law. And so this is the formula that comes out of it. This is how I had learned it. Delta H1. And write that on the side here. I don't know if I write it later, but delta H1 is the sum of all the individual processes. So this is the sum of all the adenizations and ionizations that you have done to get everything into a gas ion. That's what delta H1 represents. So it's one thing, but it's actually many. And I can't tell you how many terms you have. Why? Because it depends on what your charges are. If you have a +1 charge, you only have one ionization energy to add. If you have a +2 charge, it means you have 2 ionization energies to add, right? Same thing for electron affinities. It could be 1 or 2. And Cambridge was very nice to tell us they'd limit us to either +1 or +2 and -1, -2, so they wouldn't go any further than that. And then, of course, if you needed to rearrange the sulfur lattice energy, you can do that by moving this over. We'll do that in math. But the idea is that all of these energy changes all together add up to the overall energy change of the reaction. And so
Damage wasn't Hess's law or something else.
Hess's law is for all energy changes, they're energy cycles. This classifies as this is an energy cycle, isn't it? This classifies as an energy cycle. It is an application of Hess's law. And so this is the same idea that I already said what to do. The idea is that you're going to add all your numbers together, though, to get delta H1 this time. So this is another way of looking at it, but I like looking at the chart directly. Let's take a look at our first math question. It says, from the textbook, calculate the lattice enthalpy of sodium chloride given the following values. So what would we have to have for this? First of all, what should we do? I would write the overall reaction. What's the overall reaction that's being described? So we want to calculate the lattice energy, but the overall reaction for all of these are actually the enthalpy of formation. So I would write the enthalpy of formation reaction actually first, which is Na solid, which we saw this earlier, plus Cl2. How many Cls? It's a half, right? And then NaCl solid. That's our overall reaction. If you know your overall reaction, this tells you what you need to know about if you need to multiply by anything. You are making 1 sodium. So are all the factors with sodium good at kilojoule per 1 mole? Yeah. You are making 1 chlorine. So are all of the factors with chlorine good at kilojoule per 1 mole? So this is simple. Well, you know, we always start with the simplest examples first. And so how would we get delta H1? Because remember the equation is delta H1 plus delta HF equals delta H1 plus delta H lattice, is delta HF. All of the sums of what we did to get to the overall enthalpy of reaction. That's the equation. So what's delta H1? What would we have to do? We would need this number. Do you agree? So I'd start with that one. 107. Why are we starting with that? This is the atomization of sodium. What comes next? You atomize chlorine. 122. What do you add next? So remember, everything that I'm about to do here is delta H1. What comes next? I ionize sodium, right? So 496. What comes next? I ionize chlorine. Negative 348. All of this together is delta H1. Does that make sense? The sum of all my turning into gas and the sum of taking and removing electrons. So add all of these numbers together, see what you get. I'll get my calculator out. Might have left my nice one at home, but the Casio is nice enough. I did do this earlier though. I got positive 377. Let me know if that's good. 377 equals delta H1. What other number do we have? Got this, and we've got this. So this ends up being my equation. Once I figured out delta H1, plug it in. So you get 377 plus delta H lattice, which is that negative factor, we don't know what it is yet, equals the overall enthalpy of the reaction, which is what? Negative 411. So how do we solve for delta H lattice? Subtract 377 by each side. And you get delta H lat equals negative 411 plus 377. And I got 788 from these objects. Negative 788. And what is the correct unit for that? Kilojoules per, so kilojoules per mole. Everything here is the energy change per mole. Here it's per mole of that compound formed, the lattice enthalpy. Does that answer make sense? Is that consistent with what we learned in theory? Should the lattice enthalpy be negative? And should it be pretty largely negative? So this is consistent with what we know. So if you do the math and you get a lattice energy that's like positive 2000, do it again. Do it again or you're cooked, right? Just saying, right? All right, so this was an easy example from the textbook about as simple as they could make it. We're gonna, of course, do more. We've got plenty more we can do. Ready? Next example. When I was solving it last night, I noticed that I put the empty space at the top of the example. So if you want to use the top of the example to work it out, you can. What's the formula here? But I'm going to write on this slide because I need to be able to see the numbers. So what's the formula to calculate, let's say, enthalpy with given all my atomizations and ionizations? Memorize the formula. So, or make the whole chart and describe each of the processes, your choice. Do you have to make the chart to do the calculation? No, but the chart helps you understand. Like understanding, going through the chart helps you understand up, 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 and then down. Like why it's positive, why it's negative. So numbers are given to you. Delta H1 plus delta H lattice equals delta HF. Should this be a formula, you should go ahead and add to your repertoire of things you need to memorize. You either need to work it out from the formula or you need to work it out from the chart. Your choice. They describe the same thing. Here, how do we get delta H1? I'm going to get delta H1 first. I'll write it like this. What numbers am I looking for? And is there something I should consider first before I start plugging in numbers? What should I consider first? What's the overall reaction? Because I did that in the first one, right? Before I start plugging in numbers, because this is where, like I said, if we make a mistake, we're going to make a mistake plugging in the numbers. And it's because we're not going to consider our amounts correctly. And so what's the overall reaction for forming Na2S? Na solid plus and it's actually 2 Na solids. And it's up to you how you want to go about it. You could use sulfur's typical standard state, which is S8, and do 1/8 S8. Or Cambridge allows for sulfur for you to just say S, and I'm not sure why. But it does make the math easier for you to just say S solid. And then this becomes Na2 S solid. You probably look up one. Not interested. Why do I want to do this? Why am I pointing this out? How many moles of sodium? So every factor with sodium is going to be multiplied by 2, because every single one of these is kilojoules per 1 mole. Does that make sense? So that's why it's important I point that out, because that's where we're going to mess up. I promise you, if you mess up in the math, it's right there. I know from my many years of teaching the class. All right, so what do we start with here? We're going to plug in numbers for delta H1. Gonna be atomized first, right? So 107, just 107 times 2. So 107 times 2. And you can put the positive there because the sign force matters. Positive. What else do I need to atomize? Sulfur. I have one in my product, so that's fine. Plus 278. Are we okay with that just being 278?
No.
No? Why not?
Because sulfur's standard state is SC.
But you're making S1 of the compound.
Yeah, but Cambridge is from the future.
But regardless, if it was S8, it still doesn't matter. Because if you had chosen to do 1/8 S8, you still end up with 1 sulfur.
Oh.
Does that make sense? Like it's really just that matters. How many you're making. Okay, I'll just leave that one right there just in case if it makes you feel better. Not wrong. But they accept just doing the 1 single sulfur. All right, what's next? I did atomize sodium. I atomized my sulfur, so now I need my ionization energy. So plus 496 times 2. Okay. Now what? Ionize my sulfur by adding electrons to it. Negative 200, but is that good enough or do I need something else? Because sulfur has a -2 charge. So I need that one too, plus it's 40. Add all those numbers. So is there a chance you punch your numbers in the calculator wrong here? There's definitely a chance, right? We don't want that to happen, but it totally could happen. Check me and see if you get the same thing. When I solved it, I got 1,884.
1,934.
Which one? You got 1924?
Yeah, I got
That means my math was probably wrong in the calculator somewhere. Let me double check. That's what I wrote last night. Oh, did I write 230? 2 minus 200 plus, that's what I said, check my math. 278 plus 496.
Did you like get confused by your own math? It's like
Sometimes.
because you did these parentheses.
It's not parentheses, it was just like I punched a number in the calculator wrong. I believe I accidentally wrote 238. 3 and 7 are right. I don't know. But I think I wrote 238. 1921. But that is the math that results in that. And talking about the test, which you got to remind me to get back to you. Remind me to get back to you. Unfortunately, if this is a 2-mark question and we make one math mistake by punching a number wrong in the calculator, we lost a mark, right? I was telling a few people, one of the things you may consider doing on the next test is run it twice. Like put it in the calculator twice and see if your answers are consistent, right? Just to make sure you didn't punch the numbers wrong, because that's a lot of numbers. Punch in, mistakes happen. You don't want the mistake to cost you a mark on a Cambridge exam. Are we okay? Would that be nice? Is that the answer though? So 1924 plus delta H lattice equals delta H F. Do we have that? Negative 364.8. So, how do we solve? 1924 both sides. And we get delta H lattice is minus negative 2288.8. How would we round that for significant figures? I would either say negative 2290 or even negative 2289 is fine. 3 or 4 significant figures.
Do we have to round?
You should. Don't give too many numbers. Like if you go crazy and you write 6 or 7 numbers, they make
6
like
or
a whole
7?
point. Yeah, for significant figures. Just saying. My gosh. All right. Do we get the concept here though? Like what's going on? What you have to do?
Is it number 67 a new trend or something?
It is children around the world. All right. I want to. I think we have time for at least one more, right? At least one more. One more for sure. See if you can try it. I just worked through 2 with you, right? See if you can try it. Use it. Oh, it's asking for, be careful what it's asking for though. It's asking for delta H. So it's the same equation, but this time you have delta H1 and delta H lattice. So see if you can try it. I'll give you another 5 minutes. Is 5 minutes too much time, too little?
We should have like 6, 7 minutes.
5 is good.
Good morning, teachers and students. Please pardon this interruption. Teachers, just an advice. We are starting the filming process for our recruitment video, and we are going around classrooms starting in the next couple of minutes. So thank you so much for your flexibility and allowing us to showcase your wonderful things happening in the classroom.
For us, I think it's going to be looking at math. Oh my goodness. All right, 4 minutes. I should probably set up my bell work for praise too. Are you restarting it to do the other one? All right. Anybody have an answer you'd like me to check, or we're all still working on it?
We need next to it.
You don't know if we need science to
My lord. It's the best we need to do that too. I don't know. Maybe we'll find out.
Why? But why would you not multiply by 2?
Oh, because
You review again, right?
because CO2, you have to make lots of C. That makes CO2 to be back to stay at CI. That's only one.
All right, 2.5 more minutes. Yeah. Just tell me to do a quick check.
Like, you're going-
You're just adding that factor in. Basically. All right. You do have to show, one of the marks is to show the numbers. So if you don't show what numbers you're plugging in your calculator, if you have the right answer, you would only earn 1 out of 2 marks, I believe. If I told you you didn't get the right answer, pay careful attention because I'm going to be going over the answer very shortly.
Wait, that's 6, 7.
One more minute.
Sorry.
Yes. All right, 1 minute, 1 minute. For those of you still working, see if you can get the answer. Yes.
Yeah, but 90.
Yes. Same thing I did earlier. Frustrating. Those are the things, that's why I said, kind of usually twice, like check your numbers. But it's not that the process is difficult, it's that there's so many numbers that it's very easy to miss one or type something in the calculator wrong. All right, so let's go ahead and go review this question. And then remember, I do have your test to get back to you in the last 5 minutes of class.
Please pardon this interruption. Seniors, this is a final reminder that if you are going to retake an 8th class exam that you did not pass in June, I need to know today. I need to know by lunchtime, which is at 10:30. I cannot extend it any longer. School date, SAT, I'm going to move it up to earlier in October so that you have a score for your November 1st deadline. So if you do want to take a school day SAT, I need you guys to pay for it. The deadline is next Friday. So let me know so that I can order your exams. Thank you.
Okay, I want to bring up something here before we get started. When you're looking at the compound formula, you can predict everything for the equations, meaning you can predict how many of each atom you need. You need 1 calcium and you need 2 chlorines, right? And you should also know the charges because the charges tell you how many ionization energies you need to add in and how many electron affinities you need to add in. So now let's take a look at the question. We need to find delta H1. So first we're going to atomize our calcium. What number is that? I get 193. I'm going to use that first. So 193. Do I multiply that by anything? No, because there's only 1 calcium in the formula, right? So then we go on to, let's see, I don't know, chlorine. So what is the atomization of chlorine? 121. But that's for 1. We are making 2. So you must multiply 121 times 2. Then, what's next? Ionization energies, right? How many do I need? I need both of these. So I need to add 590 and I need to add 1150 because that gets us the calcium plus 2. And then I only need the first electron affinity for chlorine. However, there are 2 of them. So that could consider that. That gives me my delta H1. You could, like what I did was I just added the lattice to that because it's literally delta H1, then you add in your delta H lattice, right? And that gives you your delta HS. So what I did was I said, okay, that's delta H1, all of this. And then I just added in, okay, what's my lattice, right? And all of that together gives you the final answer, which is negative 790. There's no moving an algebra equation around because that literally just gives you delta F negative 790. And I need to address 1 mark is for showing all the numbers. You do not have to label all the numbers, but you have to show them, like what you're adding, what you're subtracting. So this is the bare minimum that you have to do to get the 2 marks. Like literally just write out the set of numbers with when you multiply by 2 or when you don't.
Yeah.
So I think that it's about 9:20, so that should close out today's lesson. However, I do have your test to give back to you. So I'll be giving you back your test. I want you to look over them for the last few minutes of class.
You keep them?
You keep them, just like last year. You keep them to study off of for quarterlies and for end of year Cambridge exams. These are being given out in no specific order. I shuffled them. Highest mark was 37.
7.
I do have. I just told you what I got, and I'm pretty sure it's that. If you want to do the last question in the assignment, you can in the lesson. It's up to you. Starting with Imani, check over your test. Daniel, check over your test. Analia, check over your test. Haley, check over your test. Andrea, Moreno. Omar, to check out your test.
I don't know. Are they gonna do what do you
Isaac, to check out your test.
Who would be the sponsor for that?
Yeah.
No, that's why I'm like,
Chelsea, check out your test. Over your test. So look over any feedback comments I gave you.
Or like you underestimate.
Alexander Bencoco. Isabella.
A failure.
For your test.
Absolute failure. Only getting 36 marks.
Ashley.
I have to go down next time. Don't see.
Samuel. Sabrina.
I also got 36 marks.
Really nice.
Ahmed.
Jesus.
It's wrong because
Negative 348.
they asked you which one was the structure of the two F's. Equation for that.
Oh, wait.
3.75 lower PKH stronger.
Look.
Equation's right. It's,
Oh yeah. It's up there.
but it's not. That's what you're asking.
No, how
Hey.
Yeah.
failure. Wait, is this something worth it?
Danny.
I saw your smallest.
I'm sorry? Yes, have a break.
I told you Indy.
There is no way.
Ramon not here.
I
Atza.
forgot to do negative log of this.
Work out. Thought this would work.
Look, I forgot to do negative log of this. I actually. Gosh, I got gosh.
You didn't know.
Realize.
Oh yeah, I did not. I didn't even know how.
I mean, I don't think. Jesus Christ.
Oh,
I mean,
I did write commentary.
yeah. Damn. I mean, it could be -2 though, right?
Remember when salt just goes directly through you and takes your bones out? You know?
Look,
I was thinking the last one.
I read that.
Yo.
I read that. You were gonna less wood. That's why I wrote it.
No, I'm good.
Oh yeah, I said you know how it is.
If you want that one more time, I will.
I was like, oh, this is the same question, and I was like, you got that from me. Sometimes they give me questions. Hi. You're gonna be in class.
All right, get there when we get.
The former previous period, that's like that. I have questions. Yeah, you can get them in the back. Something. Sophia and Stefan, you put the game back, right? Thank you. Yeah, I have 2 office days, so I'll just set them up right now. So the regular kids, they're going to be doing a bell work, which is on technology. They'll be using tech for the bell work, and then I can set them up. Yes. Nicole, do you need me? Okay. All right. Thank you. All right.
Don't worry about it because that was
Those days, Haley, I'll talk to.
Miss, I didn't get my
You didn't take it on time, so it's not with everybody. So you'll get it at maybe at some point after I
Just.
take the. Because remember, I grade everything at the same time. It's okay. You just don't get it back at the same time.
Well, I'm locking for
Oh, you're right.
If I didn't email you, that means I don't have a sign up for mail. So for the spot brush,
Yeah.
and you did or didn't get an email.
I got it. Shit.
You
But
can come hang out at the booth
if
and help. Yes.
if like I have to be there before.
No. 10:30, 10:50, and 10:50 to 11:10.
Did you get not for plumbers, but for the other 3 things?
Somebody said maybe Luke, so maybe.
Okay.
I don't know who filled out maybe Luke.
Okay.
Like, why would you put maybe next to your name?
To be honest, I told
Miss, I
some
did
people
that
to
too.
sign up for me because I didn't have my phone.
Oh yeah, I did see maybe Caesar at some point. Yes.
What shift am I in?
You have to check the email.
This.
And Jose wrote it on the board in the meeting, like, okay, that's true.
This.
So check the email.
Yeah, I'll check the email.
This.
I sent an email to everyone.
Yeah, I remember getting it, and I saw my name was on it.
Check your
but I
email.
don't-
Wait, Francesca, you did posse interview in front or Wednesday?
Bye.
Sign to those postings where they have to actually sign.
I did go. It's like,
Just check one thing and then I'll let you all in. Hello.
Morning.
So you're in the classroom, but I'm not. That's interesting. Oh, okay. Like I only have a few minutes to go to the bathroom. You should have let me know you were staying.
I was getting the table set up and stuff. How you have it all cute.
I'm sorry?
He was getting like the table set up.
Oh, okay, no problem. Alrighty. Let me at least tell that there's people
Okay.
already in here, okay? As I let them in.
Go for it.
All right, so remember today's a review day. There are people in the back, they're gonna be recording some things in the class. They're doing marketing for magnet recruitment today, so I'm just letting you know. You don't need to change anything meaning. Go ahead and get signed in for the bell work and turn in your homework in the first few minutes of class. And Kaylee and Jose, I'll be talking to you very shortly. All right. Good morning. Good morning. Come on in. Morning. Morning. No, I think this is possible.
I'll see you there.
Yeah, today's a review already.
All right. Ponte. Says she signed a media release form that she's
That's fine.
that does not.
Yep,
send.
we just let them know. You got it?
Yeah.
Oh.
Where is she gonna be sitting?
The second, that second table? Okay. Yeah, no problem.
That's fine.
We
but
just
we're
let
gonna
them
be
know and
capturing
they
the kids
will-
doing the experiment.
Right.
Well,
You're-
the activity.
The
okay.
activity, yeah.
Or-
Sure. All right, Jose and Kaylee. Well, it was a weird time because I didn't tell them what to do.
Yeah, go for it.
No, that's fine.
How long before? How long do you think? That could take you a few minutes.
That's fine. You got-
No, how long before you're coming? How was on the break? We're doing first.
We got another classroom to go to? Yeah.
Come back in like it's
Yes. Fine.
Don't worry.
How you doing, Jake?
Good, how are you? Yeah, the full, yours.
The spirit shake.
Okay, that's fine.
That's fine.
That's fine when we come back. Make sure to take it off. Okay.
In the hard mode, you're gonna do. And we'll get, Freeze is when you keep it so that you can, understand. No, this is that. All right, so that works good for that. They go into 8 and then 5 cars. For everybody here in the back, in the front, you should be turning in your homework. You should be getting signed in to Google Classroom and then to the bell work. We're gonna get started in just a couple of minutes. You're on home again, that's right. No to left today. No to left. Good, right? Yes. Yeah.
I have a question. If I put it in class or after the day after.
It's the day after.
Okay. So if I record that.
Don't stress. Don't stress. Like one assignment grade does not, like, if I put it in an media grade, would not even stress. Like, don't stress. Grab a calculator. You need a calculator for the bell work today. Remember, half-life equations require the use of a calculator, and that's what our primary practice for the beginning of class is going to be. It's mainly on half-life, which is what we learned last class. Don't forget there was homework that's due today. If you do have any questions about it, you can always keep that out to ask me. And you can ask me during the bell work or at the beginning of lunch. I know that a few people were confused with some of the homework questions. That's why I'm bringing it up. We're gonna get started with the bell work in just a minute. So basically it would be 8.
So 8.
Yeah. 8. I don't know if they fit, but
I think they do.
but that's what they said. There you go. Yes. And you both have your IDs on, right? Okay, awesome. Alrighty, so we are about to begin the bell work. Please make sure you are signed in for the bell work. In the first half of class, we're going to do some practice review, different activities. I'll see how long the bell work takes, depending on that. We'll probably do a gym kit review as well to practice. When we come back from lunch, I'm going to give you the extra credit study packet, and then we have a game in the back that I've prepared for you as well. And so you'll be playing a game in the back today. Jose and Kaylee are, playing it right now. And I'll be teaching you that, and you'll be playing that. It's about building the structure of the atom and linking that to chemical symbols, which is a major thing you're going to need to be able to do for the test next class. Yes. You'll get that information after lunch. All right, so we're going to go ahead and get started with the bell work now. Remember that you should have your phones away. Please make sure your phones are away. You can listen to music always during the bell work time, just so you're aware. But your only tech, if you're using a phone for using it for Wayground, that's fine. But otherwise, it should be put away. All right, so let's go ahead and get started now. My sound's on. And so basically, you play carpet, and you don't put it over. You never shuffle? So we can and until verified score. And the added department